Here they give you the molar mass of some substances, which we didn't really talk about last time. We talked about formula mass and molecular mass. We're going to talk about moles today. So what you'll find out today as we talk about moles is that the molar mass, the formula mass, and the molecular mass are all the same number. You get those from adding the masses, the average masses together on the periodic tables for the elements that are involved in that compound. The formula mass and molecular mass have units of AMU, right? Because that is how heavy an individual molecule is, or an individual atom. And AMU is a very small unit. It tells me the mass of basically one proton or neutron. Molar mass is the mass of a mole, which is a specific number of molecules or atoms, and it's a huge number, which we'll talk about today. So if you see a number in grams per mole, which is the mass in grams, which you might measure in the lab, if you had a mole of something, which is just a huge number of these things, it's the same number expressed in AMU. So if you look at this question, it's giving me sulfur hexafluoride, and it's giving me the molar mass of 146 grams per mole. If you see grams per mole, that's the number of grams, 146 grams equal to 1 mole, right? So when we talked about back in chapter 1, we started doing conversions. If you're given information that's 1 unit per another unit, that's a relationship, and you can use that to do conversions. We'll do some today. But you also know, if you see these units, the same number is also the relationship in AMUs per molecule. So if I have one individual molecule with 146 AMUs, if I have a mole of molecules, which is a huge number of them, then I have 146 grams. So then the neon has a molar mass of 20 grams per mole. Not sure why they only gave us 1 sig fig there. So this would be the molecular mass. So the molar mass of neon, 20 grams per mole. Just give it 2 sig figs in case it affects our calculation. And if we have one individual atom, then we would have the atomic mass, which we talked about earlier in the semester. It's the same number, it's just AMUs per atom. Right, so we're getting these numbers from the periodic table. The periodic table gives us, on average, if I had an average atom of neon, its atomic mass would be 20 AMUs. If I had a sample of neon with lots and lots of atoms, then on average, if I had a mole of those atoms, which is just a specific number, just like the word dozen is a specific word that means a specific number, 12, the word mole means a specific number. If I had this specific number of neon atoms, to make a mole of neon, it would be 20 grams. So the question then says, the average kinetic energies of these two gases at the same temperature are the same. Explain. So I put this in here because this is something that students really have trouble with. The relationship between average kinetic energy and the temperature. And that is that they're both measuring the same thing. So the question says, these two gases are at the same temperature. So temperature measures the average kinetic energy. Those two things are equal. So if two things are at the same temperature, they have to be at the same average kinetic energy. That is completely regardless of the state of matter, the identity of the substance. That's what temperature measures, the average kinetic energy. Kinetic energy includes vibration, for the particles, rotation of the particles if they're rotating in space or the bonds are rotating around the single bonds, and translation, which in this context refers to the type of motion where a particle is flying through space. So gases express all of those types of motion. Liquids express all of those types of motion, but solids mostly just express the kinetic energy they have in the form of vibration. But if you have a solid at a higher temperature than a liquid or a gas, it has more kinetic energy. If some solid samples at a really high temperature, it has a ton of vibration for the individual particles, because that's what temperature measures, is the average amount of kinetic energy. And those are the three forms of kinetic energy that molecules express their motion in. So they have the same kinetic energy, and that's really what that question is all about. Recognizing that's what temperature measures. That's part of the kinetic molecular theory that we introduced at the beginning of class last time. The idea that the average motion or the average kinetic energy of the particles is measured by or represented by the temperature of the sample. So when you think about substances with different masses, the SF6 is much heavier than the neon. If they're at the same temperature, they have the same average kinetic energy. We also know that kinetic energy is equal to 1/2 of the mass times the velocity or speed squared. This is just for the translational component of the kinetic energy. So if we forget about the vibration and the rotation of the particles for a moment, we just think about the speed with which they're flying through space. That component, if both samples are a gas, then it's a fair comparison to say, let's compare the speed of one sample of gas flying through space versus another. So if I have these two as gases, if they're at the same temperature, they have the same kinetic energy. That means when I take the mass of one and multiply it by 1/2 times its speed squared, I have to get the same number if I did that for the other gas. Since they're at the same temperature, they have the same kinetic energy. So if one is heavier, and I plug that number in here, so if I increase the mass, then the speed at which it's flying through space would have to decrease so that I get the same answer when I put the smaller mass in. Right? So gases with different masses, if they're at the same temperature, will have different speeds. But the reason for that is so that they will have the same kinetic energy if they're at the same temperature. If I have these two gases at different temperatures, then I don't necessarily know which has a faster speed. Because if the heavier gas is at a higher temperature, it has more kinetic energy than the other gas, it might have a faster speed depending on what the actual temperatures are.